Electricity is everywhere, an invisible force that shapes our modern world. It's so pervasive that we often take it for granted, but it's the lifeblood of our technological society. It powers your screen, bringing information and entertainment to your fingertips. From the glow of your monitor to the vibrant display of your smartphone, electricity is the silent enabler. It cooks your food, transforming raw ingredients into delicious meals with the touch of a button. Electric stoves, microwaves, and ovens rely on the precise control of electrical energy to deliver consistent and convenient cooking. It lights your world, banishing darkness and creating safe, productive environments. From the soft glow of a bedside lamp to the bright illumination of streetlights, electricity keeps the world turning, even after the sun goes down. And incredibly, it even runs your brain. The complex network of neurons in your brain communicates through electrical signals, allowing you to think, feel, and experience the world around you. But what is it really? What is this mysterious force that powers our lives in so many ways? It feels like magic when you flip a switch, a simple action with an immediate and seemingly inexplicable result. And a light turns on, instantly transforming darkness into light, filling the room with a warm and inviting glow. But it's pure science. There's no magic involved, just the elegant and predictable laws of physics at work. At its core, beneath the surface of our everyday experiences, electricity is the movement of tiny particles called electric charges. These charges are the fundamental building blocks of electrical phenomena. These charges are part of the universe's building blocks, atoms, the smallest units of matter that retain the chemical properties of an element. When these charged particles move, when they flow in a coordinated manner, we get electric current, the flow of electrical charge through a conductor. This electric current is the energy we use every day to power our homes, businesses, and industries. Electricity isn't mystical. It's not some ethereal force beyond our comprehension. It's the controlled movement of unimaginably small particles, guided by the laws of physics and harnessed by human ingenuity. To understand it, to truly grasp the nature of electricity, we need to zoom in, way in, to the atomic level, to the realm of protons, neutrons, and electrons. Everything you see and touch is made of atoms, from the chair you're sitting on to the air you're breathing. And inside those atoms is where electricity begins, where the fundamental forces of nature give rise to the phenomena we observe. The behavior of these tiny particles, their interactions and movements, is the key to how massive power grids, spanning continents and delivering vast amounts of energy, deliver energy to your home, powering your lights, appliances, and devices. We're about to shrink down to the atomic level, embarking on a journey into the microscopic world and meet the main players in this electrical story: electrons, protons, and the forces that govern their behavior. You'll see how the same principles that power a flashlight, a simple and portable source of light, also power entire cities, illuminating skylines and enabling the complex functions of modern urban life. It's all about getting very small things to move where we want them to go, controlling the flow of electrons to create useful energy. So let's dive in, let's begin our exploration of the fascinating world of electricity and discover the real science behind electricity, unraveling the mysteries of this fundamental force of nature. By the end, as we journey through the world of atoms and electrons, you'll see electricity isn't magic. It's not an unknowable force. It's the dance of particles, a beautiful and intricate interplay of forces and charges, and you can understand it, you can unlock the secrets of this essential element of our universe. Let's get started. Let's embark on this exciting journey of discovery together. Let's dive into the atom, the fundamental building block of all matter. Understanding the atom is key to unlocking the secrets of electricity. It's often described as a miniature solar system, with particles orbiting a central core. At the center, holding almost all of the atom's mass, is the nucleus, packed tightly with protons, which carry a positive charge, and neutrons, which, as their name suggests, are neutral, carrying no charge. Orbiting the nucleus, at various energy levels, are electrons, much smaller and lighter than protons and neutrons, each electron carrying a negative charge. These charges are fundamental to understanding electrical behavior. In a stable, balanced atom, the number of protons in the nucleus precisely equals the number of electrons orbiting it, making the atom electrically neutral overall. This balance is crucial. The positive protons in the nucleus exert an attractive force, pulling on the negative electrons, keeping the atom together in a cohesive structure. This electromagnetic force is what binds the atom. But the electrons residing in the outermost shell, furthest from the nucleus, these are the valence electrons. They play a special role, are less tightly held by the nucleus's pull. With just a little push of energy, these valence electrons can gain enough energy to leave their parent atom altogether and move around freely within a material. In materials like copper, a common electrical conductor, these valence electrons are so loosely attached to their atoms they can easily jump from one atom to the next, creating a flow. This sea or cloud of free electrons constantly in motion is precisely what allows electric current to flow so readily. Without these highly mobile electrons, capable of moving freely, electricity as we know it simply wouldn't exist. They're the essential messengers carrying energy efficiently through wires and powering countless devices. The ability of these electrons to break free from their atomic bonds and move is the very foundation upon which all of electricity is built. So, the next time you think of electricity and its power, remember these restless electrons, constantly in motion, always ready and willing to move and carry energy. It's their incredible journey that powers everything, quite literally, from your smartphone to your refrigerator, keeping your food cold. The fascinating story of electricity all begins with the atom, and most importantly, the freedom of its outer electrons to roam. That's the fundamental secret behind every electrical spark and every brightly glowing light. Now, with this understanding of the atom, let's delve deeper and see how these charges interact with each other to create electrical phenomena. Opposites attract, likes repel, that's the basic rule of electric charge. Positive and negative charges pull together like charges push apart. In a wire, if one end has extra electrons and the other has fewer electrons are pushed to move. This movement is electric current. It's not that one electron races from start to finish, it's more like a chain reaction, with electrons bumping each other along. The effect of this flow, energy transfer, travels almost instantly, even though individual electrons move slowly. The number of electrons passing a point per second is the current. All of this is driven by attraction and repulsion, creating electrical pressure that gets electrons moving. That's how we harness electrical energy. For electricity to do work, electrons need a complete, unbroken path, a circuit. Think of it as a racetrack. If there's a break, the race stops. A basic circuit has three parts: a power source, a path, and a load. The power source, like a battery, creates electrical pressure, pushing electrons from the negative to the positive terminal. Wires, the path, connect everything, letting electrons flow. The load, like a bulb or motor, uses the energy, converting it to light, heat, or motion. The load resists the flow, so electrons give up energy as they pass through. After the load, electrons return to the power source, completing the loop. If the circuit is broken, the flow stops instantly. That's what a switch does. Open or close the path. Every device you use relies on this simple loop. Circuits are the highways for electricity. To understand circuits, you need to know voltage, current, and resistance. Voltage is the push, the electrical pressure from the power source. The higher the voltage, the more energy each electron carries. Current is the flow, the number of electrons passing a point each second. High current means lots of electrons moving, low current means just a few. Resistance is how much a material opposes the flow, like friction for electrons. Conductors like copper have low resistance. Insulators like rubber have high resistance. The load in a circuit, like a bulb, is a resistor, converting electrical energy into light or heat. Voltage is measured in volts, current in amps, resistance in ohms. These three work together to control how electricity moves and what it can do. Understanding them is the key to every electrical device. They're the building blocks of all electronics. Next, let's see how they're connected. Ohm's law is the most important rule in electronics. It links voltage, current, and resistance in a simple formula. V equals sign IXR. Think of voltage as water pressure, current as flow, and resistance as the pipe's narrowness. If you want more flow through a narrow pipe, you need more pressure. If you know any two values, you can find the third. Rearranged, I equals sign V, R, current equals voltage divided by resistance, or R equals sign V, I, resistance equals voltage divided by current. For example, if a flashlight uses a 3-volt battery and 0.5 amps, the resistance is 6 ohms. Ohm's law lets you design and troubleshoot any circuit. It's the foundation for electricians, engineers, and hobbyists. Every device you use follows this rule. It's the first tool in the electrical toolbox. Ohm's law is everywhere, from light bulbs to stereos. In a light bulb, a thin tungsten filament resists the flow, heating up and glowing when current passes through. The voltage from your wall outlet and the filament's resistance set the current, making the bulb shine. Turn a stereo's volume knob and you're adjusting a variable resistor. Lower resistance lets more current reach the speakers. Louder sound. Higher resistance means less current. Quieter sound. Dimmer switches, fan speed controls, and more all use this principle. Every time you adjust a knob or switch, you're changing resistance and controlling current. Ohm's law is at work in every device you use. It's not just theory, it's practical, everyday science. You use it even if you don't realize it. The same rules power everything from toasters to smartphones. A toaster's heating elements are high-resistance wires. When you complete the circuit, they heat up and toast your bread. A fuse is a safety device, a thin wire that melts if too much current flows, breaking the circuit and preventing fires. Your smartphone runs on low voltage and carefully controlled current. Its circuits are designed for efficiency, using just enough power for each component. The charger transforms high-voltage AC from the wall into low-voltage DC your phone can use. It's all about managing voltage, current, and resistance to keep devices safe and efficient. From the brute force of a toaster to the delicate dance in a microchip, the same principles apply. Every device is a clever application of these simple rules. Electricity's rules are universal. Understanding electricity isn't just an abstract science confined to textbooks and laboratories. It's a fundamental aspect of modern life, deeply intertwined with our daily routines, and crucial for ensuring our safety and well-being. Every device, from the simple act of turning on lights to charging our phones, relies on the principles of voltage, current, and resistance working in harmony. Knowing these basics not only helps you appreciate the intricate technology that surrounds you, making life easier and more connected, but more importantly, it empowers you to keep yourself and your loved ones safe from potential hazards. Electricity is a powerful force, but it can be dangerous if misused or not respected. Voltage is the force that pushes current, the flow of electrical charge, through your body, and your body's resistance, its opposition to that flow, determines just how much current actually passes through you. That's precisely why water and electricity are such a deadly mix, a combination to always avoid. Water dramatically lowers your body's resistance, allowing a much larger and potentially lethal current to flow, significantly increasing the risk of electrical shock. This fundamental knowledge empowers you to use technology not only effectively, but also wisely and safely, minimizing risks and maximizing benefits. When a light bulb burns out unexpectedly, or a phone charger gets unusually warm during use, you'll have a better understanding of the underlying reasons behind it. You'll be able to confidently read appliance labels and truly understand what those seemingly cryptic volts and amps measurements actually signify. You transform from a passive consumer into an informed and empowered user, capable of making safer and more conscious choices. The story of electricity is not just about circuits and wires. It's a captivating story of human curiosity, relentless experimentation, and groundbreaking ingenuity. So the next time you reach out to flip a light switch, take a moment to remember that it's not some kind of inexplicable magic at play, but rather a testament to the power of science. And now, you're in on the secret too.